I'm the senior manager of Golden Malting for Molson Coors in Golden, Colorado. I'll be your moderator for this morning, so thank you all for joining us. The emerging topics in malt session will be the next several speakers. So we're going to start out sharing some ongoing research on how to get the most out of your barley and malts, addressing emerging challenges. As a reminder, speaker introductions will be brief throughout the conference to be mindful of time, but all the bios can be found along with the program online. Our first speaker I'll introduce is Harmonie Bettenhausen, faculty lecturer at James B. Beam Institute for Kentucky Spirits at the University of Kentucky. And she's going to be sharing her latest insight on mitigating GN and EC risk. So Harmonie, welcome on.
Good morning, everybody. Everybody have a good evening. You guys, listen. I now lecture for a living, so you guys are going to have to be a little more upbeat for me. Also, I don't care if you want to ask questions in the middle of this presentation. Just raise your hand and I'll address that. So I'm Harmonie. I know a lot of you. For those of you who don't know me, I am at the James B. Beam Institute for Kentucky Spirits at the University of Kentucky. I was formerly at Hartwick for several years as the director of the research lab up there. But I am happy to be here now. This is some research that we've been working on for a while now to try to address the issue, which has been an issue for a very long time since, first addressed in the late 80s and 90s, ethyl carbamate in distilled spirits. Oh no. Oh, we got romantic lighting. So, okay. So, can I get a little show of hands here? Who understands, who has been involved in glycosidic, nitrile, ethyl carbamate stuff? Nicholas. Okay. So, all right. So I've got a little bit of an overview, and this figure here comes from a paper we recently published on the topic, and there have been several papers published on this topic. So glycosidic nitriles come from barley. Glycosidic nitriles in general are a plant defense mechanism. There are 5 of them that have been identified in barley. Epiheterodendron is one that uses the cyanogenic pathway as its plant defense mechanism. Basically, when it is under attack from an insect or something like that, as the insect is chewing on it, it breaks open the little vacuoles in the leaves and shoots of the plant. And this little entity right here, epiheterodendron, is cleaved by the beta-glucosidase that is released. It's an enzyme. It's cleaved, and then it basically turns into a little cyanide bomb and repels the pest. So that's the plant defense mechanism. So when we're talking about taking barley through the malting process, we have found that we have seen increases in the amount of this particular epiheterodendron through the malting process, time, temperature, humidity, things like that. There's also a paper written on that, authored in part by Hannah. And I'm sorry, Hannah Ullman now? Okay, sorry. You all know Hannah. So that was all identified in the malting process. So that was one place we found increases in glycosidic nitrile. So then when we take that into the, into the distilling process, we have to deal with it there. So through fermentation, there is some beta-glucosidase, which is that enzyme, and that is inactive at mashing temperatures, but then new enzyme is introduced from yeast through arginine metabolism. And we'll talk about a little bit about that later because it does come into a little bit of play. So then after fermentation, we have a compound called isobutyraldehyde cyanohydrin, or IBAC. And then we've got that little molecule floating around right after fermentation. And then when we throw it into the still, And it is this molecule in particular is exposed to heat from the distillation process because we're creating heat, right? We have a conversion over to hydrogen cyanide. So then that's all floating around and that's volatile, right? And then when we have exposure in the still or in our doubler, and I'll talk about those terms, and we have reaction with ethanol and copper, that hydrogen cyanide turns into ethyl carbamate or urethane. So there we have the whole process, right? That's how we get there. So ethyl carbamate has been regulated in a few countries. In this country, we don't. It's not very regulated. There are suggested amounts, and distillers have targets that they go for. We're looking for under 125 ppb. This is a carcinogen. That's why we're concerned about it. It's a problem for export markets, but it's also just a problem for general health. And we know everybody's concerned about your health these days, right? So the barley-derived precursors are one of the few controllable upstream intervention points that we have. So what's been going on agronomically? Well, we heard about some of it yesterday. Top Shelf out of the Oregon State program has been picked up. It's been commercialized. It's been scaled. It's being used by people. Odyssey for a long time has been used. There are several European varieties that have been used, and people have been picking up different varieties. To my knowledge, Odyssey and Top Shelf are still the only AMBA approved ones. Oh, it's not yet. Sorry, it's not yet. It's getting there. It's getting there. And then we've got Genie on the list too. And I know that Zach Gaines is sadly not here today, but we've had several conversations about what Genie means. It's considered an ultra low, so not an actual low, but it does kind of perform the same as the rest of those barleys. So Buddha 12 is out of UC Davis, and that has been picked up predominantly by Admiral Malting. I guess we're in California, here in California, but mostly centered around brewing. And this isn't really a brewing problem, so brewers don't really care about this. But it is, we do have varieties available, but they are sort of unevenly scaled. We have varieties sitting, ready, waiting to be scaled, and people not, really picking them up. And then, we have been, I will admit, I have several conversations with several breeders. Nick barely picks up the phone anymore when I call, but about what we're kind of doing to get more into the rotation, because a lot of these varieties, even not top shelf, but we were talking about full pint yesterday, and not that was all an accident, but it wasn't really a consideration until it was. And all that to say, the European varieties are really focused on not only brewing, but Scotch production, which doesn't have the same specifications that our bourbon producers have. So that's a big deal. Getting a variety in that meets all of the specs that our bourbon producers are asking for. So a little bit about what we're doing alongside agronomics and testing and stuff that I'll get into. We have also, in order to get our collective stuff together in the distilling industry, because a lot of the times the distilling industry, lab people, wonderful people, they sometimes come from brewing, they come from oil and gas, they come from a lot of different places. And we don't yet really have standardized, validated methods for distilling. We've got them for brewing, and the distillers like to, grab from here and grab from there, but everybody's kind of doing a little bit of something. So what we're doing through ASBC is we have formed finally the distilling subcommittee, and we've gotten a lot of lab people together from all over the distilling industry and some from the brewing industry to work on validating methods and standardized reporting, because a lot of what we also find is people aren't speaking the same language, of course, and they're reporting different things. A lot of what we've run into, and I'm going to really make some people mad here at 8:30 in the morning, but a lot of what we've run into, Yari is looking at me already right now, I see it, but and this is sort of fine, but it's sort of not, right? Like a lot of the times the malt houses report averages, they report lots. But when we're trying to solve the problem, specifically this GN EC problem, we need real numbers. We need all the numbers, we need real numbers. So part of us trying to educate the distillers is having them also argue with their malt houses about needing real numbers. And I'm sure that has made some people mad, but it's all about getting this problem solved, right? So the other thing we're working on, and this is part of one of our postdocs work, is intermediate formation. I talked about that IBAC. So we're trying to look at all of the molecules and how they travel throughout the system. Because one of the problems, as per usual, is that we don't know a lot about our starting material. What our starting material is doing, when it is being transformed. We just have these vague sort of notions right now of what's happening and when. And a little bit about what was going on in the 90s when this was first identified is the distilleries were like, oh no, what do we do? Well, one of the things, and I just talked about it in the diagram, is copper contact. But we didn't know much about where and when the copper should go, how much contact it should be, or whatever. So everybody kind of just shoved copper a lot of different places. And whatever worked. Some distilleries still have that same copper in place. Some have put copper mesh, some put copper pieces, some have it at specific points in the still, some have it in the doubler. So there's not a whole lot of rhyme or reason, and we'd like to look into a little more of that copper contact situation. But we can only do that by identifying a lot more of the intermediate formations. So as for the data that I have, so this is a little malt quality. You can take a gander at this while I'm telling you about the varieties. So we had two trials going on at the same time. One was lab scale in my lab, and the other one was pilot scale. For context, at the Institute, we have a pilot scale distillery. It's about a 500 gallon still, or a 500 gallon system. We get about 1 barrel of new make out a day. So it's very small, but it's for research purposes only. So the lab scale involved the Thunder as our positive control, the top shelf, the VAR. We also had a higher protein top shelf, and then UC Tahoe and UC Capet, and then a very random variety that was sent to us by Westland Distilling. It came from the WSU Bread Lab. We don't know what the variety is, but that's neither here nor there. And then in our pilot study, we used Odyssey, our pilot positive, Genie, and Butta 12. And for most of the, I think all of the lab scale stuff, we owe a hearty round of applause to Scott Fisk for being the best micro malter in the entire world and doing this all for me. I call him a lot of favors for this research, so thank you to everybody, especially Scott, for malting all of those barleys for me. But so you can see that these are all varying. And the things a bourbon distiller would look at are not the things a brewer would look at, right? Like, we've got our protein, they're all pretty variable. Our diastatic power, which is what is very important, diastatic power and alpha amylase to our bourbon distillers, they have to be as high as humanly possible. I don't know if Dr. Elston is actually still in the room. She could tell you a little bit about her spec, which is very high. Our bourbon distillers have very high specs that our maltsters need to meet. And that's becoming a little more of a challenge, and it's been a challenge in these new varieties. So anyway, we did a little lab scale distillation, and this is my my undergrad researcher, Carter. He's done all this work. We made some little tiny bourbons, very reproducible little bourbons, and looked at, one of my questions was about processing behavior. Not only about the EC behavior, but the processing behavior. We wanted to know if immediately things were going to process well through our system, because the last thing the bourbon producers want is any sort of stuck mashes or things not working because the enzymes just weren't there, right? Because a lot of our, some of the distilleries use exogenous enzymes, but James Beam does not. So we have to, sort of consider that. And we did not use any enzymes in any of these studies. Does anybody have any questions? No questions so far. Okay. All right, so results from the lab scale stuff. So we've got low wines here, and these were taken at 50 proof. This is a little bit lower than normal, lower than we would see on our system. But for context, low wines are the first thing that comes off of the still. They're a little bit impure and might need a second pass. So you can see here on the left, we've got our little individual varieties. Here we've got the Odyssey top shelf high protein, Vivar, and then on the right, it's just the pooled results. So remember I said that the limit that people are looking for is like 125 or below, right? So these are some pretty low amounts. We've got some copper contact in this coming off of our low wines, which has converted the hydrogen cyanide over, but we still have EC here. So, this kind of suggests that the low wines represent a pooling and concentration step going on. For the high wines, which is our second pass, the alcohol has become more pure. The impurities have been taken out with that second pass. It's a higher proof, 135 proof, and this is fairly normal. We can see on the right now the individual varieties. There's a little bit more there. We had more data on those. All of the varieties that we looked at, and again, those are very low amounts. This is a scale from 8 to 12, so very low amounts, right? And you can see the GN positive control there, a little bit higher on the high wines. Okay, fine, that's all normal. And these are, again, very low amounts. All this to say, yes, the GN nulls are doing their job, but why is the EC still present? I'm not going to speculate on that right now. So for the pilot scale distilling, same thing. We've got our low wines, a little bit higher proof, but still considered low wines. The pooled on the left and the individual varieties on the right. Again, very small amounts. A little addition to this one was that we had a phone call in the middle of this from someone in Canada, a maltster in Canada, asking us about DRAM, if we knew anything about DRAM and how was DRAM performing. And DRAM's a fairly new GN0 variety, right? And they're like, well, we're still seeing ethyl carbamate. Like, we are too. So join the club. So they sent us some DRAM pretty late in the game. They sent us both malt and some already processed material for us to look at. But what's interesting here is the spread. That's what I find interesting on this, and that's what I find interesting on this, the high wines from the pilot scale distilling. Not so much that it's there, but because it is effectively lowering the EC risk. Because I will tell you that the lab and the pilot scale distilling in a very controlled environment does not represent what's going on in the real world. Those numbers out there are much higher because of the variance in the system. Distilleries are all very different. So these are these data. I'm not going to say much or speculate about what's going on yet here. But what is interesting to me is the spread and the fact that the GM control is the same. The GM positive control has the same spread as some of the GN nulls. So it's not a bad thing. Again, they're very small numbers, but still there. I don't really want to talk about that. So processing differences. How many of you have been to distilleries at all, like bourbon distilleries, Bourbon Trail, anything? You guys need to come down. So you walk into one bourbon distillery and you're like, oh, this is really cool. This is really pretty. They show you all the equipment. They're like, here's our column still. Here's our doubler. It works this way. And then you walk into another distillery and it's different. And to my point earlier, everybody has copper in different places. So that copper contact times, temperatures, those are all different depending on the distillery that you go to. So, despite the fact that we've got some pretty consistent lab and pilot scale results, our distillery is very controlled and it's very clean. One of the things that we've discovered that we put in the paper was that it's important to clean your copper. Otherwise, you risk losing contact with copper, right? So you have to be cleaning it. And that has cleaned the situation up quite a bit. But like I said, people have copper in all different types of places in their distilleries. And everybody's process is different. People are using different mash bills, different barleys, things like that. So all of these variables play into kind of what we're seeing. One of the things we found had an effect on EC, and this was done with Castle and Key, and they were using GN positive variety. I think it was like 1.4 or so. We discovered that where the wash is fed into the column still really makes a difference as to how much EC comes out. That, again, comes down to copper contact. So the way the column still works, right, is you've got steam on the bottom. and the beer is fed up top, right? And through counter pressure, ethanol evaporates, other things, everything's got a boiling point. Things are volatilizing off, being recondensed into low wines. And then we've got the little thing called the doubler, which again serves as a sort of a second pass distillation point. And then those are recondensed into what are our high wines. That was a very, very simplified, non-engineering way to talk about the column, but it matters where you feed the beer into the column as to how much EC you are going to get out of it because of that copper contact. So higher point, less copper contact, lower point, lower copper contact. So one of the things we don't know much about, speaking of unreacted species, the hydrogen cyanide going into the barrel, we just don't know how much has been already, has had the reaction and has fallen out. Ethyl carbamate should, because of the copper contact, fall out because it's non-volatile and go out with the stillage. But we have a lot of unreacted species that go into the barrel, and that has not been measured. The unreacted hydrogen cyanide does convert to EC over the first several months in the barrel, but we don't know what happens over time because we've just started all of these studies and just been able to look at all of these variables. We also know, evaporation of water and ethanol does enrich the non-volatile EC in the barrel, but again, something that hasn't been quantified. We have found, of course, higher, a distiller will have something on the shelf and their report of what the EC was before it was bottled is different than, sometimes after. So all of that is very interesting. And we are, of course, this is one of the factors we need to look at. But the question for me, and again, still low amounts, the GN0s are doing exactly what we need them to be doing. There is still EC. And again, very varying amounts, depending on where you are, what variety you have. You saw the spread and the differences in those individual varieties. And again, we don't have enough of these varieties. We need more of these varieties to go around. So we've got the epiheterodendron, GN pathway suppressed, but that residual ethyl carbamate may possibly reflect the yeast nitrogen metabolism rather than the raw material cyanogenic precursors. So I'm going to bring you back to this fun diagram brought to us by Drs. Patty Aaron and Zhang Yin when they were at RAR. This work was done. And people have profiled more amino acids since, but the point in me putting this up is that we just don't follow it enough. We've got all new varieties. We've got new processing situations. We have extreme environments, growing conditions. And I know that Dr. Fox is going to talk about a lot of that and how that affects proteins and starches. Well, it also affects amino acid composition, right? We know that yeast take amino acids up preferentially. And we're looking specifically at the arginine pathway here because I mentioned earlier that was part of the formation of urea and citrulline. Well, urea, when it is, so very simply, when the yeast takes that up and it is very stressed, usually it doesn't come back, it reassimilates it. But there is a possibility that it is being not retaken up and that urea is sticking around and through the interaction with heat and ethanol, of course, in the barrel, we are forming ethyl carbamate through a different pathway. So again, trying not to speculate here, but it is something we're taking a different look at because why not? So all of that, we have about 8 million questions in this research, of course. And we're very grateful for everybody who has been our cooperator in this research. We really need to do several things. Look at the copper effects in the doubler, liquid levels, contact time, vapor, liquid copper, looking at our cistern EC targets that ensure, of course, compliance at bottling, and even looking at things after bottling. We don't know much about those maturation and concentration effects. Looking at the GN-driven versus the fermentation-driven EC formation, we'll see. And a lot of our bourbon producers are looking at degree of modification, of course, our different varieties, when and where they put the malted barley in, things like that. So we've got a lot of work to do, and of course, not many answers right now. But I would like to thank everybody, and I'm sure I've forgotten some people who have been specifically involved in this research. Of course, our partners at Makers and Jim Beam and Suntory Global, Castle and Key Malt Europe, Admiral, Great Western, my undergrad, Westland, our postdoc Taylor, Dr. Brad Barron, and of course, Scott Fisk and the whole team at Oregon State. They've been really integral in all of this and very supportive of this research. So with that, I will take any questions.
All right. Thank you, Harmonie. Do we have any questions?
I didn't make you mad, and of course.
Thanks, Harmonie. Great presentation. So you talked a little bit about copper placement, and I wonder how much you've looked at. You talked about copper in the still itself, but considering copper in the downward pathways and what that can mean as far as washing those precursors into your new make and what that means for
So some people, I think what you're talking about is copper placement elsewhere besides the actual column still, right? So another placement, and there are a number of placements we can't really talk about that distilleries have, but one of those is in the doubler. So that is after the column. So that's just another place that it can come into contact. So you saw the difference between the low and the high white. So that doubler is the difference. There is some copper contact there. And people have been looking at it, yes, but there's a little bit a lack of data, a little more anecdotal data right now, and we're trying to capture real data about it. So yeah, it is something we're looking at. Thank you for that.
Other questions?
Harmonie. Hi.
Hi.
Hey, Harmonie. Thank you for the presentation. It's great. Just a question. I'm very ignorant when it comes to distilling, so pardon my question, but if you would have data there that doesn't go through copper, so meaning dirty or no copper at all, what would be the effect of a null GN and the EC versus GN positive?
Yeah, so I mean, there would be no reaction if there's no copper, right? But that's kind of not the point. I had this discussion yesterday with someone else, and there would be no reaction. And people do distill, well, anyway, that's not the point. But the copper has another place besides just the EC, right? The copper helps to scavenge sulfur compounds. It very much affects flavor and quality of the spirit. So that's one of the reasons for it. So you can't just have no copper. It wouldn't react at all. Yeah. But you would also have really terrible distillate. Yeah.
And a real quick yes/no question. Has anybody studied whether there's an effect on the plant losing that ability to fight off bugs?
We just talked about this. Is Lexi here? Lexi had an experience last year, I think.
It was, I guess almost 2 years ago now, where I was trying to run a rapid generation cycle in the greenhouse for our families that had GN0 parents. And essentially, they got attacked by caterpillars in the greenhouse, which we've never seen in our greenhouses before. But what was interesting was they targeted certain plants and left some unavailable or like untouched. So Nick and I think that they do have, that may have something to do with it, considering that's the only thing that was different about those families was we were targeting GN0s with them.
Yeah, we just don't know. I mean, Dr. Hayes, assured us that nothing really was going to happen, but that was, in one environment. So when we're putting these varieties into different environments, we just don't know yet. We just don't know what the effect is really going to be. So it's just something to keep an eye on. I mean, more research questions.
All right, last question here before we move on.
Thank you, Harmony. My question is, with barley varieties, if you don't malt them and just completely enzymatically convert the starches and ferment that, do you still have, has anybody looked at ethyl carbamate or these products in that situation?
With unmalted.
Because this is a germination-induced thing, isn't it?
Yeah, it is. Yeah, it is. Those are in.
It's the malted stuff that's the problem.
Yeah. To my knowledge, I don't think anybody has particularly looked at that, but that's not exactly the recipe. And I said earlier, there are distilleries that will not use exogenous enzymes, so that's not really.
Right, but I'm getting more at the basic question of, are those precursors coming just from the barley variety and the environment, have nothing to do with the malting process?
No, they do have something to do with the malting process. It's the malting process that exacerbates that. I mean, it still has the propensity. Those glycosidic nitriles are stored in the germ, in the embryo, so they're there. But it's the process of malting, again, the heat, the humidity, the time, temperature, all of that allows that to be formed.
All right, thank you. We're going to cut off questions. Appreciate